Okay, our next speaker is Henrik Sandberg. It's our great pleasure to have him in this summer school. A bit about Henrik. Henrik is full professor and at KTH at the Department of Decisions and Control. Henrik received his postmaster and PhD from Lund University, not far away from Copenhagen, and then moved to KTH. But before, you were a postdoc at Caltech,
Yes.
and then you had some visiting periods at MIT, Australian National University, and University of Melbourne. Henrik is a very leading researcher in the area of cyber physical resiliency and in control. And he's also IEEE fellow member. So yeah, we are very interested to hear your talk about cyber physical security in energy systems. Stage is yours.
Well, thank you very much, Alal, for this very kind invite to speak here in this very nice summer school. I'm very impressed by the lectures I've seen so far, so I'm a bit under pressure here, I feel. Yeah, first of all, I'm really a controls engineer, not really a power engineer. I have worked quite a bit with power systems examples. So this is a topic we've been working on for the, let's say, past 10, 15 years. So it's a relatively new area at the intersection of controls and security. So what I will share with you today is a bit of what the lessons learned, and hopefully also that you can see that it's relevant to your area. I've not really worked on market systems and so on, but from what I've seen here and discussions with Jalal, I think it's a really interesting topic also to think about the implications of security in those type of systems. I really hope that you can interrupt me, since I'm not exactly sure what type of background you have in terms of controls and dynamics. There will be quite a bit of that. So I feel free to interrupt me during my lecture here. It will be, I think, better for everybody. So this is what I had in mind for the talk. So part one is CPS security. It's a bit of an overview. Maybe you would think it's a bit superficial, but it's a bit about what we've learned for the past 10 years or so. What are the challenges? What are the problems? Why do we care? There will be 3 case studies. I think 2 of them at least from the energy sector, so you will hopefully recognize those. And then in the second part after the break, then it will be more details. So there, I cannot cover everything what we're doing. So I chose to look into a little bit into how we think about attacks in these contexts. How do you model what the cyber attack can do in a control system? So I will focus on denial of service attacks and what is called false data injection attacks. And I think that's something that could also be interesting for market manipulation, for instance, even though I will not talk about that. So we'll talk a bit about what is called unknown state and input estimation. We'll talk about cumulative sum tests and principal component analysis, how to detect deviations in signals, if there's some sort of coordinated strategic manipulations going on, etc. So that's what I had in mind. We'll see how far we get. Yes, lots of people to thank here. Former postdocs and colleagues. I'm not going to read all their names here. Many of them have spent time with us at KTH. So yeah, great. A lot of their material you will see today. A lot of references to their work, and just by themselves or just in collaboration with us. Okay, so cyber physical system. So what do I mean by that? It's one of these terms that is flying around everywhere. We use it a lot. In the context of this talk, this is what I mean. It's industrial control system. So it's basically the IT system that is being used to sort of coordinate and monitor a physical infrastructure. And that's what you have here at the bottom layer. So in our case, you can think about the power grid. It could be a transmission grid or maybe a distribution grid. But a very similar IT structure is used in many other infrastructures. You can see some of them here, transportation networks or gas and power, gas and water, etc. So there's a physical underlying infrastructure. And then there are some layers of equipment above it. So you have these local stations, PLCs, that carries out actuation and sensing on the infrastructure locally. I guess in the power grid you would talk about the remote station, RTUs. So it's basically a substation that has the ability to measure locally voltages and frequencies maybe and actuate on the grid. On top of that, you usually have a homogeneous communication infrastructure. Typically, it's being owned by the system operator, but not always. Sometimes they rent communication lines. So it can be a fiber network dedicated, or it can be a microwave links, etc. It's typically quite heterogeneous. So it communicates information to a control center where there's a human typically sitting looking at these type of workstations, where they collect all the information from this large system, and they make some sort of overall decisions and recommendations for the system to operate. There's also what is called an application server and historian server, basically just recording a lot of the data, what is going on. So that's basically the person who is making sure everything is working in the system. Then typically what you have is a firewall, an IT basically a firewall between these control systems and the corporate IT system. So that this is where basically the office, the CEO, etc. sits. They want to know basically what's the operational data, how much power are we selling, etc. So they can also connect to the control system center, but usually, hopefully, done by the through a firewall. And then you see here also an external communication, and that could be the internet. So this is more or less typically how these infrastructures look like, whether it's a power system, a water system, or whatever. And that's somehow, this is the cyber physical system we're going to talk about. So you see where the physics is at the bottom, and all of this below here is all the IT in between. And we will talk about cyber attacks in this context. So cyber physical system can mean other things as well. If you look in the literature, it can mean autonomous vehicles, it can mean drones, cars driving around, etc. They're also subject to attack, etc. I will not talk much about that. There's also a lot of talking about now that you want to control loops over cloud infrastructures. So you're buying a control service from Amazon, and you're basically submitting your sensor data to the cloud and closing the loop. That's, of course, also opening up a lot of security issues. But as I said, I mean, today I will mostly talk about the infrastructure to the left. So what I'm going to do now, it's going to show you some of examples now of cyber attacks in this context. And maybe the first one, it's usually where the history starts. You maybe have heard about this before. Stuxnet. Have you heard about Stuxnet? Is that something Jalal has? Yeah, most of you have. Nevertheless, I can go through it very quickly. So there's even a movie about it. It's called 0 Days. It's actually quite an interesting movie about the history, about the attack. Yeah, you can see. Sorry, I got a phone call here. So what was the problem with the Stuxnet? Well, it was a cyber attack, and it was targeting a very particular infrastructure, namely an uranium enrichment facility in Iran, I think in Natanz, which you may have heard about in the news lately because I think it's been bombed. But already in 2010, it was being subject to cyber attacks. And the reason it was being detected was that people found this Stuxnet malware in Windows computers, and in particular in so-called Siemens Step 7. So that's a particular Siemens system designed for industrial control systems. So they started to find all over in Europe this very infectious worm, but it didn't do anything. It was just sitting there. And then they were reverse engineering it and see what is it actually doing. It turned out that it was a very advanced piece of malware, because it used, first of all, 4 zero-day flaws. It basically means that this malware, they used 4 previously unknown weaknesses in the system. So typically, if you find a weakness in an IT system, you exploit it once, basically, because it opens one hole. But here they basically wasted 4 pieces of knowledge to design something. So it basically shows that this was something very special they were doing. And as I said, the malware didn't do anything unless it found exactly a very particular type of physical infrastructure. So most of the time where it was found in Europe, it didn't do anything. It was just basically sitting there. And when it was being reconstructed, what the attack was doing, I can tell you, I can move this pointer. I don't know why it's sitting there. So. When they reconstructed what this malware was doing, it's basically, this is how one thinks that it entered the system. So it's believed that somebody put in a USB stick somewhere in the Natanz infrastructure and in an office computer somewhere. And then this malware basically worked its way through all this infrastructure until it found a PLC. So that's a programmable logic controller. And there it basically checked what piece of equipment is being controlled by this PLC. And if it wasn't the right thing, it didn't do anything, it just sat there. But if it happened to be this variable frequency drive, so this is really the uranium enrichment facility, so it's a high frequency centrifuge that you have to control it at a very specific frequency, and it's then being used to get the right concentration of uranium. So once it found that equipment, what it started to do, it was starting to record sensor data under normal operation. So it basically collected a large batch of data of that type. And then at a specific point in time, what it started to do was to replay that normal data back up to the control center. And then it had knowledge about this physical device. So it's a very, I don't know how big it is physically, but it has some resonance frequencies. It's a mechanical device that has a rotation, rotates very quickly. So it knew about exactly what resonance frequency this device had. So it started to actuate on that particular resonance frequency. So basically what was happening then was on the factory floor, these centrifuges started to vibrate and break. But at the same time, the human operator was sitting in the control center and everything was green. So they didn't see anything bad, right? So it was basically taking out a lot of this. So this was in 2010, and this was kind of a starting point for this area. It became clear that there is something going on here. There are people with a lot of resources that knows a lot about these systems, and they can basically launch the type of attack remotely. And this movie that I mentioned here, it's about, it's supposed to be a joint Israeli-US operation, but I guess they have not confirmed it. But this movie I mentioned, the 0 Days movie, is about the backstory for this. So that's an interesting piece of work. Now, what has happened since? That was in 2010. There's been many, many more malwares being found, and they often get these type of interesting names. Here's another malware that was found in 2017. It's called a Triton malware. And why do I bring this up? It's because it was targeting Schneider Triconex safety controllers. And why is that interesting? Well, it's a lot of critical infrastructure. They have often a parallel control system. So they have the normal control system that sits there and do the normal operation. But then in parallel, they have these safety controllers, typically maybe in nuclear reactors, etc. Something goes wrong with the normal system, the safety controllers are supposed to step in and make sure that nothing explodes. They should not sit on the same IT infrastructure. They should sort of be separate. They should be very, very hard to update software in them, etc., etc. So they should be very, very safe. But still, this Triton malware was found, I think it was in Saudi Arabia. And this is from, I think it's from McAfee, the security company, who basically wrote a piece about how this malware was being found. And today, I don't think anybody knows how they managed to put this Triton malware on the safety control system. I think it was some sort of oil infrastructure in Saudi Arabia. So it shows that there are very advanced malwares around. There are people with a lot of resources that they can put that malware on your systems. So didn't do anything here, so it wasn't activated, but it was sitting there and basically waiting for to be active. Yeah, so here you see more reports of malwares. Different names. I will shortly talk about the Indestroyer one. That's also an interesting piece. Moving on to a third example, events in Ukraine, 2015. So this is well before the war started. So this is a news piece that there was a coordinated hacking attack that caused a Ukrainian power outage. So what happened here was that somebody managed to take remote control of the control center for a distribution grid. So the human operator basically was sitting there, and suddenly the cursor started to move around and clicked on substation and opened circuit breakers. And the human operator couldn't do anything. And after it had opened the breakers, it basically started to erase all the software in the entire control center to basically make it very hard to do anything. So this was in 2015 and before any war, but of course Russia was being accused of this. There's another piece, this is from New York Times, saying that United States has infiltrated the Russian power system, so they have lots of malware just sitting there and waiting for basically to activate this attack. So it really seems to be part of this the way you conduct wars nowadays. Here's more about this attack against the Ukrainian systems. So what I talked about before was the called black energy. So that was what happens in 2015. So what a remote access to the control room. So basically somebody was sitting at the other end and basically moving around their mouse and opening circuit breaker. But since then, there's been much more advanced cyber attacks in Ukraine, and this is the Indestroyer malwares. And this is an interesting piece of paper by a colleague, Cardenas, as in students. They basically have somehow they got access to this malware, and they created a sandbox, like a separate IT system. So they basically was able to run these malwares in a power system simulator in a coordinated manner. So this is a very interesting paper, basically explaining exactly how these malwares operate. But you see here the Indestroyer, the latest generation of that piece of malware, it's fully autonomous. So whereas in 2015, 2016, there was basically a person conducting the attack in real time, this is a fully autonomous piece of malware that is basically similar to the Stuxnet. It's basically you put the malware somewhere in the system, it starts to work its way through the IT infrastructure until it finds the equipment it's interested in. It sits there, and at a given time, it basically starts to actuate some sort of harmful signal. In this case, it's open and closed circuit breakers in a particular pattern in a coordinated manner. So that's the Indestroyer 2. So in that paper, you can read much more about exactly how it works, and I mean, they even found bugs in the code, etc. It's quite an interesting read. So, what is really the problem here that we're thinking about? I mean, one could think like this sounds like very simple attacks that if you just install some sort of normal IT security that you probably have already on your office computer. Why don't you do that in these systems? Well, I'd say that this figure shows a bit what the problem is. I mean, there are two things. A lot of these control systems are there for safety. They're really about protect humans from damage, and that's the overall goal. So the system should be very sort of simple, predictable, they should follow specifications, etc. Security traditionally has been a little bit the other way around, right? You want to put password protections, making sure that you don't have unauthorized access, etc. So typically, security and safety are different sets of people. They don't really often, not always talk together, talk to each other. So somehow it's conflicting goals here. And traditionally, the control systems have been seen as closed infrastructures. There's no real security threats. You saw the examples, that's no longer true. But I would say that this type of safety mentality is really what has been governing this type of systems. Here is a little cartoon from my colleague Alvaro again, talking a little bit about the different type of people that they basically think that this type of problem is not really my problem, it's your problem. So the control engineer says that, well, security, that's the IT guy's job, right? And then the security guy says, well, that's like a safety thing that you should do. And that somehow it falls in between. That has been sort of the I think prevailing mentality. There has been, this is just some a reference. If you're interested in security in general, you want to get to know more about this. This is a very nice initiative, the CyBOK initiative. I think it's being run from Manchester University. So they put together like reports compiling the state of arts of different areas of security. You can see here different areas that you might care about. And there is one here on cyber physical systems, which that cartoon was taken from. Here is the report. This is Alvaro's, who wrote the report. I was part of the reviewing committee of it, and it's a very nice sort of introduction. It has lots and lots of examples and pointers here and there. So if this is something you're interested in, I would really recommend you to have a look at this report. It's available for free. There's also this presentation slides that gives you a very quick introduction to it. So that's an online resource. There's another online resource that might be interested, MITRE. It's a US organization, and they has basically collected a lot of different attack vectors for different types of IT systems. And they have also introduced now a collection for industrial control systems. So here you can see the most common type of attack vectors that have been found in industrial control systems. You can click through there and see. So that's another online resource. Okay, let's take some, I need some water. So that was a little bit of the setup. So let's talk a little about what we can do about this. How do we model these things, and how can we improve the situation, and leading up to what we call risk management. So first, let's talk a bit about CIA. So CIA in information security. Have you heard about that? What you think you know what CIA is? No. Well, it's there's three properties in security usually you care about. So it's the confidentiality. So in our context, in a control loop, what would the confidentiality mean? It's basically a privacy problem. I think it was being mentioned as a problem yesterday, actually. So this is a classical sort of property that you want from a secure system. So if you like, in our type of systems, you could think about this as a problem like you have a physical plant, so it's a power grid, and you send now a vector of information. So it could be the power consumption in your system. You communicate that over a network, and it's being received by a control center. So if it's possible for an adversary to read that data, then you have violated the confidentiality. So then you've lost that property. So that's one key property you care about. So C, that's the C in CIA. So that's one thing we care about. Another thing we care about is the integrity. So that is basically that you reverse the arrow. So if you violate the integrity of a system, what you basically mean is that what the power plant is sending to the control center, it's not what's being received. And this is an attack vector that we will talk much more about in part 2. So the adversary is able to change the message content. So that's a violation of integrity. And finally, the A is the availability. If you violate the availability, it basically means that the packet of information that you send, it doesn't really it's not being received. So classical attacks usually violate one of these three properties. All of them are relevant in our context. Typically, what I will talk more about in part 2 is mainly the integrity and availability attacks. Why is that? Well, it's because in a feedback system you're closing a loop over a physical system. So that means that you affect the physics. So if you turn, for instance, an availability attack means that the control command doesn't reach the plant. And of course, that means that it can start to go in the wrong direction. So that causes physical damage. With that said, there's a lot of confidentiality problems as well, especially with these type of attackers I was talking about that have a lot of resources. There are signs that the attackers has been present in these systems maybe for years before the attack is being conducted. And what they're doing during that time is really about violating confidentiality. They're really collecting a lot of information, learning models, how does the system work, etc. So I'd say all the three of these properties is something we should care about. Yes. Yeah, here's a list of typical vulnerabilities that you find in systems today. And these, you may think this is really stupid. Why hasn't this been solved, this type of problems? It's really about this safety security, that it's a safety problem that has been solved initially and that has been hanging over. So typically computers in these type of systems, they have no antivirus or intrusion detection. USB ports might be accessible. Hopefully nowadays, and the awareness is much higher, so it's better than before, but for a long time it's been like this. There's communication links, lacks basic security feature, no encryption, no authentication. Typically that's how you solve, like, protect against integrity attack, right? You authenticate your message to make sure that what you receive is actually what you send, right? That type of complexity is not something you often find in a control system because, again, the safety engineer says that's too complicated. It causes a lot of complexity in my system. It makes me harder to verify safety. There might be lack of physical protection, so people might be able to access the PLCs and RTUs. And then, of course, there's these zero-day flaws. And that's again, zero-day flaws is like previously unknown vulnerabilities in your system. And of course, that can always happen. So in a way, these type of systems are designed for an older threat landscape. So what are other challenges we have here? So one problem here is that patching and frequent updates are not well suited for control systems. So in your iPhone, you get an update every now and then. You often know maybe that it doesn't quite work the way you want to, the way after you do the update, right? So people are very updates in control systems are very infrequent, maybe once per year. So even if you know that there's a bug in your system, it's so complicated to change the IT system that you actually wait maybe for the annual update of the software. There's lots of legacy systems. These systems have developed over decades, so you have old equipment, old IT infrastructure that you can't really replace overnight, etc. So is it only negative? There are some plus positive aspects as well. So the network dynamics, if you look at the IT infrastructure for these control systems, they're often simpler as compared to an office network. I mean, an office network, there's a lot of heterogeneous activity. People are using Teams, they're using Word. It's a lot of different patterns in the communication. So it's hard to sort of what's anomalous. It's hard to say. In a control system, supposedly it's much more restricted what type of traffic you should see. It should be more regular. It's read a sensor value, compute an actuation, and send it out. It's more simpler patterns. So in that way, it should be easier to detect that something is going on. On the other hand, an attacker can very easily learn the pattern, right? It's not so, you don't have to be super smart to see, this is, if I just follow this pattern, then it's not going to trigger. So it goes both ways, this. And the topology is often much simpler as well. But that's something that you can exploit. I think I'll skip this. Yes. So what should we do? Yeah. So clearly, we really need to put in more IT security in these systems. I mean, it's not. The security people has to come into this domain. We should use encryption, authentication, lightweight solutions. I mean, that's not really something to argue about. I mean, that should happen, but it's not going to solve everything. So we'd really have this. Protecting the information is not enough. This picture here, I think, illustrates part of the problem. I mean, it really shows that these systems are closed-loop systems, right? You have a physical plant, you have sensors, you have communications, controllers, and actuators. So information is flowing around here. So if you protect one single link here, let's say you put in authentication here, it doesn't really solve the problem necessarily, right? Since everything is going around in a circle, it's really, if there is a manipulation happening at one point, there's a very high risk that it starts to sort of cause an instability in the system. So it's not only about sort of focusing on one particular communication link and say, now I've encrypted this link and now the problem is solved. There are examples, for instance, of that sensors that you can carry out physical attacks against sensors. So people have put like a magnet next to a sensor, and that causes a bias. So then it doesn't really matter if you encrypt the sensing value, right? I mean, the data is protected, but it's wrong, right? So from the control system's perspective, it doesn't really matter if that was encrypted or not. It's simply wrong, that value, and that can cause the instability in the system. Yeah, so that's what I'm saying here. Malicious action can enter anywhere. Another important aspect here, so sometimes people say, well, let's just put in more fault tolerance in the system, a lot more redundancy and so on. Yes, that's absolutely, you should do that if you have the budget. But it's important also to understand here that faults are random typically. Attacks are not random. It's really the opposite. Attackers have an intent, they have a strategy. So often I think the best way to think about this is using game theory. I mean, you have two players, the attacker and the defender, and the attacks that we look at are often coordinated, both in space and time. I will show you some examples, like how you can cause manipulations of sensing data. An attacker would not sort of just add bias on one sensor. Of course, they would do it coordinated manner in several places to cause the maximum harm. A fault detection system would not probably trigger, as you will see in an example here. So it's important to understand these differences, that you're playing against somebody that has an intent here. Yes, and finally, I mean, there's of course, if you should not put all your trust in these encryption protocols. I mean, there's frequently found bugs in them as well, right? And maybe you heard about there was bugs in the Linux AI systems, found new bugs in Linux kernel, right? So you should not only put all your trust in these type of solutions. There needs to what is called defense in depth. You should have several layers of defense against the systems. Yes. So what's the answer here? We've been advocating what we call this risk management. So what we mean by that, we should try to think about, try to enumerate which type of threat should we care about for your given infrastructure, what type of impact could you expect from these type of attacks, and then what type of resources should you put there to sort of prevent that. And that's what we call by the risk management approach. And that's not a static approach, that's something you should do all the time. The good thing is that we often have relatively good models of these systems. So we usually have very good models of the controllers because we design them ourselves. We have good models of the physical infrastructure. It's a power grid. We know the dynamics. We can put out sensors here and there. So we can often predict or simulate what will happen beforehand and try to sort of see what is bad and not so bad. Here is a plug for a paper we wrote some years ago. It's a tutorial introduction for security and privacy of cyber-physical systems. A lot of what follows here is really covered in this paper. So if you want to know a little bit more in details, I could direct you to that one. So risk. how should we think about risk in this context? So risk is a triplet. It's a scenario, it's a likelihood, and it's an impact. So the scenario is basically, what is the attack scenario you're thinking about right now? The likelihood, it's, I think, the most problematic part of this triplet. So risk often comes from safety, like what's the probability that something breaks? To me, it's a bit hard to interpret what that probability means in a security context. So there are some different interpretations available, because it's really hard to know what an attacker is thinking about, what he knows, etc. So here are some different possible interpretations of the likelihood aspect of the. So it could be, for instance, that what's the probability that an attack that started will be successful? If it's a very complicated attack you have in mind, maybe the probability by itself is pretty small. If you're really conservative, you say that the probability that an attack will happen is 1. I mean, if there is a weakness in the system, if you just wait long enough, it will happen. Another way is to say that roughly the probability is sort of 1 over the effort. So if it's an extremely complicated attack you have in mind, then the likelihood is not really that high. And then finally, you have the impact. What is the consequence of an attack? And that you can simulate, basically. You can basically see what will happen there. So that's typically how you do it. And then you can create a plot like this, and you get a lot of dots. And of course, the dots that are far away, those are the ones maybe you should care more about. So high impact, high likelihood attacks, those are maybe the ones you should care more about. So this is a risk management cycle. So what you should do is basically you should think about scenarios that could happen in your system. You do the likelihood assessment, the impact assessment. You put in some risk mitigation, and there's 3 classes of risk mitigation: prevention, detection, and treatments. And then you should basically repeat this cycle over and over again. Maybe I'll talk a bit about this. So how do we model an attack here? So first of all, there are 3 things we think about here. The attack policy. What is the goal of the attack for a scenario? Is it to destroy equipment? Is it to increase the cost? Does he want to remain undetected? Does he care about being detected? Maybe he just wants to break the system. I mean, that's kind of the goal of the attack. So that's the attack policy. Then you can ask, how much does the attacker know about the system? Does the attacker know the plant model? Because if he knows how the system works, that opens up possibility to stay undetected. And then finally, how much resources, which type of communication channels does the attacker have access to? And this is typically how we model things in a control system. We use block diagrams just to see here. So for instance, this is the attack model here. So disruption resources, that is how much writing ability, how much communication can it corrupt. So here, see if I can get this right. Here. So here is the plant, here's the feedback controller, here's a detector, here's the attacker in the middle. So the question here with disruption resources, how much ability does the attacker have in corrupting network traffic and causing sort of physical harm to the plant? Model knowledge is basically how much does the attacker know about the feedback controller, the detection system, and the plant. And finally, disclosure resources. How much information can the attacker need? Can read? Can it read all the sensing data or only part of them? So those are different axes of information. I think maybe I'll skip this in the interest of time. So those 3 information axes can be mapped then into this attack space. This is now taken from this tutorial paper I mentioned. So different type of attacks you find in the literature. So there's replay attacks, that's the Stuxnet attack I was talking about. There's denial of service attack, bias injection, undetectable attacks. They sort of span this space. So depending on how much resources the attacker have, they will fall here. And you, as I said, these paper references, you can go back to this paper here and see what they are. So how do you prevent the attacks then? Once you have identified the attacks that you want to block, prevention is basically trying to target the likelihood. So you want to decrease the likelihood, and that you can do by several things. You can do what is called watermarking, you can do coding, encryption, you can do rational security allocation, you can do confidentiality by noise injection. If you do differential privacy, for instance, you will recognize that. So that's sort of addressing the likelihood aspects of the attack. Detection is that you introduce much more sort of resources to be sensitive to perturbations. So you can do tuning your detector thresholds carefully. We'll talk more about that in the second part. You can work with your security, your state estimator. We'll talk more about that. You can do what is called moving target defense. You can use robust statistics, etc. So that's kind of another way to sort of make it harder for the attacker to actually carry out the attack. And finally, you can do the treatment. So that's sort of, if the attack still happens, how do you sort of reconfigure your system so that the damage is not as bad as you think, as it could have been. So it could, for instance, be that if you notice that some part of the equipment is being attacked, you can reconfigure the control system so that. So those are sort of the three main ways of addressing, and I cannot cover everything here, so you see I will cover a little bit more in part two. Yes? So the watermarking was actually introduced to sort of as a protection against the Stuxnet attack. So I mean, it's a pretty stupid attack if you think about it, right? You record old data, and then you replay exactly the same data. I mean, if you had a little bit smarter system, I mean, what's the probability that exactly the same sequence would happen twice, right? So it's not really a hard attack to detect. But watermarking was initiated as part of that. And the idea was more or less that the controller should superimpose a signature on the control and basically signal it through the system, so that the controller sort of should be sure that the loop is actually being closed. There is nothing sort of, the information I send into the system, it's actually coming back. And since I have a model of my physics and everything, I can predict roughly how it should look like. Of course, there is a penalty there that you're basically doing something suboptimal with respect to the control, that you're perturbing the system. But that's kind of how we think. So it's like a physical watermark, so to say, and that will sort of prevent some classes of attacks. Any other question there? Yes. Yeah. Then you have succeeded. I mean, then you have a good redundancy in your system. I mean, if so that's you would measure the impact. So then the impact would be zero. The physical impact. Typically, that's what we care about, like how much physical harm is being creating in the system. Of course, the IT system is being affected, right? So you should not sort of sit back and relax, because clearly something is happening. But in the short time scale, right, then the attack did not have any physical consequences, so you would be fine. But of course, you need to make sure that you remove that piece of attack. But that's exactly what this treatment here. So typically, what secure state estimation does, it's trying to sort of look at all the sensors and trying to see which ones are looking like they're being not in the right pattern, and if you looks like it's deviating, then you remove it. So that's really. But then you get a warning. Say, here's a signal that doesn't fit the pattern. I'm not going to use it in my control right now, but you better check out. Yeah. I think it's maybe good to have some examples now. Let's see when is the break? Is it 15 minutes? Okay, so let's do these examples then. I think that's good. So here is one of the first examples we did. So unfortunately, it's not really a power system, but I think you can think about it as a power system in the following sense. So it's an interconnection of water tanks. So you see the blue is water levels, and there's two pumps here. I guess if you want to think about this as a power system, you can think at the water level as the frequency, I think. And then the pump is how much mechanical torque you put. And if you increase the torque, like the frequency will go up. And then the leaks here is how much power you drain in the power loads. Maybe you can think about it like that. It's not perfect, but anyways. So this particular infrastructure has this. So there is a control center. There is a base station that communicates. So in this case, it was a wireless control system. So the base station communicates to a repeater. And there's control commands being sent. So basically, this is how much water you pump in this tank and in that tank, and that pump there pumps in some water there and there. And so it's a little bit of a complicated infrastructure, but I will come back to that, why we did it like this. And then there's sensing. So you only measure the water levels in the lower tanks here. So this water level here and here is not being measured, and that's important. And the controller is supposed here to regulate the water levels. The problem set up, the attack scenario now is the following, that somebody has hacked this repeater here. So it can manipulate the controls. So the controller send out how much voltage it should apply to this pump and that pump, but the repeater here is manipulating that. So it will put on something else. But the sensing information here, it's going to be fine. Let's say now that we have invested in some sort of authentication system or encryption. So they are immune. So whatever information the controller receives, it's going to be correct. But the control commands can be manipulated. So the question is, can an attack be carried out here that is sort of would not trigger any alarms? So here's a movie. This is the setup. Unfortunately, the movie is not super clear, maybe, but let's play it and then we'll see. I can try to explain. So what you see here, it's the real U. So that this is the voltages being applied to the pumps. So there's two pumps. Real Y, it's the measurements being received by the controller. Let's see if it works. No. Maybe I need to move the pointer. So. Pointer. So that's magic. Let's see if I. I don't know why it's not. Okay, maybe what I'll show you is just the. Yeah, okay, so I'll just show you what the output is here. So what is going to happen here is that when the attack starts, the attacker exponentially increase the voltages on one of the pumps and exponentially decreases the voltage on the other one. What is happening then is that the green and the blue here, that's the water levels down here. They will, when the attack starts here, they will remain more or less constant until the time. And what happens with the water tanks up here is that one of them starts to decrease until it's empty, and the other one starts to increase. So basically, what the attacker is doing here, it knows how the physics works here, and by increasing exponentially in one rate and decreasing exponentially the other way, it basically ensures that the measured variables here are unaffected. But there are other dynamics in the system that is affected. This is called zero dynamics in control systems literature. And this somehow was quite, when this was discovered some years ago, it was quite a sort of excitement, because it basically meant that you, even if you have encrypted sensors that measure, they look perfectly fine. There's really nothing to see here. The measured variables are unaffected, but there is dynamics living in the system that can be non-trivial and even unstable in this case. We could even empty the tank. Of course, what happens is that once one of the water levels here is empty, then basically the system becomes sort of, the dynamics changes dramatically, and then you will detect the attack. So here is actually the alarm signal. So the alarm is triggered for the operator when this blue signal hits the threshold. So the attack is carried out for, I don't know, is it almost a minute? And one tank is empty and one is full, and that's how long it takes before the operator sees anything. So kind of was kind of a proof of concept that you can exploit, the attacker can exploit the dynamics in their favor, even if you have perfectly sensor equipment in the yes.
It's called undetectable because the attack is aligned with physics law.
Yeah, exactly. Or in this case, I mean, the sensors, they don't really change much. I mean, the attack is designed, so the attacker knows what is being measured. So he basically creates attacks that do not affect the measured signals. So basically asks, okay, I know this, I cannot touch these sensors because I know they're going to be fine. So what room is there left? How can I maximally perturb the system? So there's nothing really that's, and this is basically the solution that you get. So this is called zero dynamics attacks. And a lot of work have been put into these type of attacks because it's kind of it's truly a dynamic phenomenon. You really need you can understand it maybe also using some linear algebra that we'll talk more about in the second part. Basically, it's a null space. You need to find the null space of your system, and that's what you're exploiting. But it's a dynamic phenomenon, and if you know a bit about control systems, I mean, really what the attacker is doing here, it's that it computes. So the attacker needs to know the model of the dynamical model of the plant. So in this case, it's the 2x2 transfer function. And then it computes the poles and what is called invariant zeros. And in this particular case, it has what is called an unstable zero direction. And that's what he triggers. He knows this, and then he uses that. So basically the attack was really hitting that unstable zero. So it was injecting this attack signal what is aligned with the zero dynamics. So that was basically what it was doing. So if you think about risk management here, if you're the operator, if you have your model like this and you see, oh, I have an unstable zero direction here, that doesn't sound good. What should I do? Any ideas? What should I do here? Any? Yeah. The system is stable. It's the zero dynamics is unstable. But okay, I sure. But indeed, but how would you do that? I mean, yeah, exactly. Or move a sensor. Yeah, exactly. So the sensors are not placed in the right place. So typically, the way to affect zero dynamics is by adding or removing sensors. So that's what you would do. Yes. So it's yeah. So in this particular attack was up here in this corner here. Here's another case study that we did. It's on power transmission state estimator, and maybe this is more aligned with what many of you are working on. So so this is supposed to be a large transmission power system with lots of RTUs. There's a SCADA network, and this is supposed to model an energy management system. And I don't know how familiar you are, but typically what is, so there's not much dynamics in these type of models because you measure maybe every few seconds. So it's more a quasi-steady state situation here. So I will not use any dynamical models here. So Y here is a collection now of voltages, power flows out in the transmission grid. It's being communicated as a long vector. It's being fed at the control center. It's being fed in what's called a state estimator, trying to figure out the voltage levels in all the nodes in the grid and also the phase angles. Then that state estimate is being used, for instance, to solve optimal power flow problems that we heard more about yesterday. It's done for continuous analysis. How should I reconfigure my grid to ensure safety? It's also used for bad data detection. And this is what I will talk a bit more about now. So bad data detection is you're trying to figure out if there's any malfunction, sensors that are not sort of fitting the patterns, etc. All of this goes to the human operator, who then decides basically how should I change the operating point on my grid, etc. So we worked in a project with a power company, and they told us when we started talking about what if there's a cyber attack here? What if an attacker infiltrates the communication network and starts to manipulate, for instance, a control command like we did in the previous case study? They told us it's not going to happen because we have this fantastic bad data detector. The system is so interconnected. There's so much redundancy in the systems that if you just start to fiddle a little bit with some, this bad data detector will trigger. That's what they told us. Of course, we were sort of, we tried to challenge that. So this is another picture showing how we thought about it. So we have this scenario that an attacker can manipulate. So Z here is the measurement. So X is the state of the power grid. H is now a nonlinear function from the state. So the state now is voltage level and phase angle in all the nodes. So we said, okay, let's think about a scenario where an attacker manipulates a subset of these measurements. That's being fed into the state estimator. And then potentially that would cause a bias in the state estimate, and that will then be fed into the optimum power flow and all these steps. And the question was now a bit, can we design attacks here and C here so that this alarm system does not trigger? That was kind of our challenge. And then we sort of looked into the case where we need to think about how the bad data detection system works. I will come back to that shortly. But it's important here to say that in this scenario, typically what you have is that you have lots of measurements, more than state. So that's what the operator told us. I mean, they have so many measurements. So the state is basically the number of nodes. But then you measure maybe power flows in both ends of links, etc. So there are lots of measurements. So that's what they said, that if you manipulate one, then I mean it's going to trigger the bad data detection because it doesn't fit the pattern. So what the bad data detection system is trying to do is basically what Jalal said. It's trying to see, is the received measurement here, is it consistent with the physical model? Is there a physical state that can reproduce these measurements? And if there's one sort of measurement that doesn't fit the pattern, then I will alarm. So that's exactly what the bad data detector does. It basically takes a state estimate, it plugs that state estimate back in the measurement model, and then it compares. It compares the received measurements with the estimated ones, and if there's a residual here, it will basically trigger. So that's kind of how it works. So what we did then was, of course, we tried to, as a malicious attacker, we tried to see how do we optimally attack such an infrastructure. And to make the attack undetectable now, what you would do then is that so A now is the attack vector. So what you would do then is that you would only consider attack vectors that are physically consistent. So that's what I mean with HC here. So H now is the Jacobian. So we linearized. We take the operating point, we take the Jacobian of the measurement model, and then we're optimizing over all physical states that are consistent with the physics. And then I say, now I want to hit sensor I. So I now is the target. So I say, let's take the the power flow measurement, the tie line between Sweden and Denmark or something like that. I wanna corrupt that measurement. And now I want to minimize the number of corrupted measurements all over the system that causes that bias, because I'm interested in manipulating as little as possible. I don't want to manipulate thousands of measurements. I want to have very few targeted measurements. And that's what alpha is here. So this symbol here is the cardinality of A. So it's a number of non-zero elements. That's what this symbol means here. And if you can code this up, it's basically a mixed integer linear program, and you can solve it for relatively large systems. So it's, in a sense, it quantifies the complexity of a least effort attacks on sensor I. So you can run this now over every single sensor, and then you get sort of a profile of the system. So for instance, if alpha 1 is equal to 2, that means that if you wanna hit infrastructure 1, then you need at least 2 corruptions. That's the minimum you would need. So yeah, in general, you can solve this using mixed interlinear programs. We have written quite a number of papers on how to solve it more efficiently. There's, if you're familiar with mean cut max flow type of graph algorithms, that you can, in the particular case of power systems, you can use such algorithms to really solve these type of problems very, very quickly. I'm not going to go into that in details, but there are several papers on that. This is just some of the benchmarks we've been looking at. So the outcome is typically of this type. So the color coding here basically shows areas where the index is lower or higher. So we frequently found cases, so in contrast to what the operator said, that there's basically impossible to manipulate. We often found like these islands, parts of the network where this index is less than 7. So even if there are like 500 sensors, there are places in the grid that you can sort of go in and make very small coordinated attacks, and you can basically drive the state estimate wherever you want. There's some theorems also that you can prove if you have this concept. This is one of them. So basically, by definition, what this means is that if you want to attack sensor I, then you need to at least have resources. You need, the number of corruptions needs to be larger. I mean, it's a theoretical minimum. It's not possible. But there are also other types of results, like that if the number of corruptions is less than half of the index, that means that you as an operator can always identify and reconstruct an attack. It's basically, if you're familiar with compressed sensing type of arguments, you may have seen similar type of. So this index tells you a bit about what security level do you have in your system. Maybe I don't go into too much detail here, but this is how it looks for how the index looks for this IEEE 118 bus system. So you see that on the x-axis here you have the measurement index. So there's 500 sensors in the system. So again, there's 118 nodes. There's 500 sensors, so it's 5 times as many sensors as states. So it seems like you should have lots of redundancy. Yes, please.
You're assuming that you know the matrix age, right?
Yeah.
Is it easy for an attacker to then know?
Yeah, that's of course that's part of the risk scenario. What you think is believable. I mean, one scenario where they would know it is, of course, H really comes from, it's the Jacobian of this one. So yeah, maybe you don't know the Jacobian of that. But on the other hand, we talked earlier about the confidentiality attacks. So let's say now that the attacker sits here now and is recording data for a year. What you get then is snapshots of vectors that lies in the range space of H. And after a while, you have probably reconstructed the range space. And it's really the range, I mean, it's really that what you need, right? I mean, if you look here, what do you need? You need to know the range space. You don't need to know, you really don't need to know Jacobian. What you need is the range space. What are patterns that fit the physics? So H here, it can be So if you think about an attack like that, maybe then it's more believable. Yeah. I don't know if it answered your question, but yeah. Yes. Yeah, I mean, it really depends what's the objective of what's the objective of the attack. I mean, if the objective of the attack is to basically just shut down the service, I mean, then there are much simpler ways to do that, right? So an attack like this is manipulating the state estimate. So coming back to this, I mean, if you want to disrupt the service, I mean, you should go for you here, right? You should open circuit breakers, right? Like the Ukrainian case. If that's what you want, sure. I mean, then this is you shouldn't try to manipulate. I mean, this is convoluted, right? But I mean, if you, let's say, you want to affect the state estimate of the operator, and you want the operator to believe that the system is in a different state for a long time, maybe you want to drive their operations in a different direction. Maybe you're a competitor, etc. So it really, coming back to the risk scenario, the scenario really specified what's the goal of the attack. Here, the goal of the attack is to create a bias in the state estimate that will not trigger any alarms. So the operator will basically run, the physical system will be somewhere else than what the human operator thinks. So if that is part of the goal, then this would make sense. Yeah. Yes. Yeah. Maybe this is just showing the, yeah. So with a plot like this, how would you use a plot like this? So here are all these indices across the system, and of course it's the sensors that has the lowest ones. Those are kind of the most weak points in the grid. Those have the least redundancy in the system. So there, that points in the grid. That's what was marked red in the plot. That's where a small coordinated attack can have a big effect. Up here, these sensors, like 18, it basically means that if you're corrupting one of those sensors, you need to, in a very coordinated manner, you need to hit 17 other devices simultaneously. So if you're going to protect this system, maybe that's not the most critical point. So again, coming back to the risk management perspective, with a plot like this, you sort of see, okay, this part of the grid, maybe if this is the scenario I care about, maybe here, this is the point I should think more about. No, it's the identity. It's the ID number. So 4 here and 7, it would map to certain points in the grid like that. So in this case, this area here, that's where the sensors are more susceptible, whereas the green ones, they are sort of more safe, so to say. Yeah. Yes. I don't remember exactly where. I think in this case, yes, there are sensors. I think there are one flow sensor in each end of each power line. Yes, I mean that you can, of course, you can put that as a. If you think about, we talked about Stackelberg type of games before. I mean you could, this optimization problem I showed you there, right? That's the attacker's problem, right? So it's the follower action. So the leader action then is to place the sensors or secure certain sensors. So that's another way to protect. I mean, one way is to just put in more sensors. Another way is to, let's say you can update the IT infrastructure. So you can invest in some sort of authentication. So you can say that some of these sensors are much more trustworthy. What that would mean is that certain sensors are immune to these type of attacks. And that can really change this a lot. I mean, just to have the most trivial example, let's say this power line here. You measure the flow in both ends. if you secure the sensor in one end, I mean, the other one for free is secured, because, I mean, if that one is being manipulated, it will immediately deviate from the secured one, right? So, and you can often find these type of pattern that I secure one sensor, and then you see in the physics that all the sensors that are being coupled to that one, they get security for free. So you can really get, if you do it in the right way, you can really put in a very small budget, and you can really sort of boost. So what happens then is that every time you secure, I mean, these indices will sort of start to go up. And of course, you would start maybe down here, and then you will start to push up. Yeah. I think we're really time for a break, I think. Yeah, maybe just one to close this. We actually tested this in a real. We got access to a real state estimator, and this is how it worked. It worked well. So we used a linear model, but the true system is nonlinear, and we basically what you can see here is that we could attack sensors with 150 megawatts. That was 55%, and there was not a single alarm in the bad data detector until the system suddenly didn't converge anymore. So it's really solving a nonlinear Newton-Raphson problem. So at this point, it basically could no longer find a solution to the but there was no alarms until that point. So it actually worked. This was some years ago. You see, 2011. So hopefully the situation is better now. But these type of linear attacks, even though the real system is nonlinear, they worked surprisingly well back then, at least. Yes. Okay. Yeah.
When was the bad data detection technique in place?
We didn't know. We just had the software. So what we did is I think it was some sort of nonlinear least squares. I mean, they were trying to take all the measurement, and they tried to fit minimizing a squared residual or something like that to find a state estimate. But I mean, they didn't tell us exactly what they were doing. We just had a human-machine interface, and then we computed an attack like this, and we started to deviate the measurements and just saw what happened to the state estimate. And yeah, this is what you see here. So yeah. I mean, typically these communications are not encrypted today, as far as I know. I mean, the protocols are typically not, the infrastructure is not open, so it's typically owned by the operator. So are there scenarios where this could happen? Yeah, I would say so. I mean, we've found several examples of malwares in the system. There's these autonomous malwares attacking in Ukraine, for instance. So I mean, it would be an easy matter for them to if once you get that malware in the system, I mean, they could corrupt these measurements like that. So I don't know if that's answering your question. I cannot say I'm aware of any. I have not heard about any attack that is doing this, but there's been a lot of academic interest. I think partly it's because it's a nice academic problem. It has a clean solution. So I'm not exactly sure how afraid we should be here, but there's been lots of work in this direction. I managed to get the video started, so I'll just show it to you to show that I didn't lie to you about it was not. So just to remind you, what this video will show you is that this is kind of the steady state. of the system, so that the water levels are all steady. What will happen then as the attack is that the lower levels that will also be steady. So it means that there's two different dynamical trajectories, one where everything is just fine, and one where two states are doing weird stuff. But some of the states are exactly the ones I happen to monitor are doing the same. So just if you now the attack starts, and now if you look carefully, you see the water levels down here. Oh, you don't see. Water levels down here, they don't really move, whereas this tank here is going up and down. So this is really a dynamical, you can see here. So the operator looking at this plot will not, I mean, there's a little bit of deviation because the model is not perfect, it's non-linear, etc. But it's not enough to trigger any alarm in this case. And as I mentioned before, I mean, of course, it's trivial to detect this attack if you just move one of the sensors to one of the other. Then you will see that one level is changing. But of course, then the question becomes, if I move one sensor up, is there another trajectory like this hiding? So that is really the problem. If I put the sensor somewhere, I need to sort of discover, is there dynamics of this type there or not? And one sensor allocation problem is more or less that put the minimal number of sensors to eliminate all of this type of harmful. So it becomes a combinatorial search over that. I also got a very good question about these attacks in the case study too. Why we think it's interesting to look at only these like small coordinated attacks. Isn't it more realistic that all sensors are being, I mean, if the attacker is there, he can just change any sensors. Sure, but again, it's a part of the attack scenario. If you look at the communication infrastructure, often there's a communication network underlying these grids, which is so there's communication links from every node. From every node, there's a communication link going into the control center. So it really depends where you think the attacker is. If the attacker is in the control center, of course, then he can change anything, and then you're doomed. But if the attacker is maybe remote out here, then it's only those local sensors that are maybe accessible to him or her. Often there's a routers, so communication links goes through routers. If the attacker is in that router, I mean, everything that goes through that router would be susceptible. So it really depends on where you put the attacker in this network. So again, it's a scenario. It's the scenario you consider. You need to take that into account. I think maybe before I go into the more mathy part of the talk, I want to talk a little bit about this final case study because I heard you had a similar system here at DTU, so maybe that's interesting. So the third case study we looked at, it's low-level attacks against local controllers. Something along this line. So it's the same type of infrastructure. What we consider here is that there's a physical infrastructure that is coupled. So it can be an electrical system. So if there's something physical is happening, if this local controller here is doing something, that there's a physical coupling to the neighboring system, so that the effect will propagate, such like in a power system, for instance. So in this particular problem we worked on, we had the following attack scenario, that some of these local controllers was infected by malware. So think about Stuxnet. Somebody has put in a USB stick in some sort of local device. But the scenario also said that at least some of these local controllers they were fine. And the whole idea then was that we want to use that some of these measurements are being okay, and then we know that there's a physical coupling. So the malicious behavior here, it can be sensed here, and it can be communicated up to the control center. In that way, you can try to mitigate some of the effects. So that was the whole idea of this paper. And the technical assumption that was required for this to work is that if you know something about control system, it's about observability. So for this to work, what you need is essentially that the entire physical, or most of the physical state, is observable from the sensors that are being okay. So enough sensors are sort of healthy, and that is being then used to mitigate the attack. And we looked at this type of attack in the Nimbus microgrid. It's in Ireland, so it's a combined heat and power unit at they have on the campus there. And you can see a little bit here about it supplies power and the heat to the campus there in Cork. And you can see here what it features. There's a wind turbine, there's a lithium battery, and there's this electrical thermal combined heat and power unit. And I heard that there was a similar thing here at DTU. And we asked the people running this, what's the most valuable thing here? What are you most afraid that will break here? And they said that this combined heat and power unit, the boiler there, that's really something that we would be afraid of. So we, in this, it was a EU project, so we worked on attack scenarios here, and I can share some information about that here in the next couple of minutes, what we did. Yes. So more or less this is how the system worked. So they have this combined heat and power plant, they have a boiler. So we looked at the heating part. So the warm water is being sent out. It goes out into the buildings, and you measure the temperatures in all the lecture rooms. It goes back. The cold water is coming back here. And now there's a sensor that measures the temperature in the outgoing temperature, and there's a sensor that measures the cold water coming back. And of course, the heat difference is a measure here of how much has been delivered to the buildings. And in this particular plant, whether they're going to start the boiler or not to heat the temperature is really depends on these measurements. And the attack scenario was that the attacker would like to break the boiler, to increase the pressure so much that it will more or less break. And one way to do that is, of course, to manipulate the sensors here. For instance, you could say that, oh, the water is very, very cold. Fire up, and then sort of just the pressure will increase. So that was kind of the scenario. But now to map to the picture I had before is that, of course, to the control center, there's much more information available. So we shouldn't really only make that critical decision based on these two sensors, because you have lots of more information. I mean, you have measurements of the building temperatures all over the campus, right? And of course, those temperatures are related to the temperature you have of the water here, right? So there's similar to the power grid. I mean, there's physical laws. It cannot happen, for instance, that the temperature here is very warm, and suddenly it's even warmer here. There must be there's a physical law. You can predict exactly how the temperature profile will change. And you should use that. When you receive these measurements, the control center should sort of check it against the physical laws and see that it works. So the adversary infects some of the field devices, what we call AT1 and 2. And the defender here, we assumed that the operator has access to all of these sensors and will try to predict that there's an attack going on here and to correct for it. So this was a block diagram of how we were picturing this to happen. So the idea is more or less that one of these sensors is being corrupted. All of the data is being communicated to the control center. The control center there's an anomaly in one of those measurements. The control center will do a state estimate. It will find that this doesn't fit the pattern. But in order to sort of still operate the system, it will say that, oh, that is an outlier. I will not use that measurement for control anymore. Instead, I will make a prediction. I have the physical model. I have sensor measurements that I believe are correct. So I make a state estimate. I predict what the measurements should have been. And then I'm going to run my control system on the prediction instead of the faulty one. So the control system is just going to sort of go through. It's going to flag this measurement as a faulty one, but it's just going to continue to control. That was the whole idea. So not very advanced. In this particular paper, we compared a lot of different type of anomaly detection strategies. We had one group working on a physics-based model. So we use system identification of the buildings just to sort of see how the correlation physically relate between the buildings, as where the input is the temperature of the water going out. We had one group using more machine learning. They were using support vector machines. So they just collected lots of operational data. They had used raw data. They used residues from the Kalman filter, and they used windward mean, etc. So we were comparing different types of detectors. I think, in the interest of time, I will not go through too much in detail. If you're interested, it's in this paper that I mentioned. One interesting question when it comes to these type of detectors is how do you know which detector is better than the other? And we were using this metric that was introduced by Urbina and Cardenas in this paper here at CCS. So if you know something about machine learning, you maybe heard about the ROC curves, where you try to decide how to tune detector thresholds and how to decide what is a good detector or not. What we've been arguing in this paper is that might not be the best metric to compare detection methods in these scenarios. So, excuse me. So for each detector, what you do instead is you get a curve, and on the x-axis you have the mean time between false alarm. So that basically means as you increase the detection threshold, you get a higher mean time between false alarms. What you have on the y-axis is really the maximum undetected attack. So what we do here is more or less the following. So for every x point here, we set the threshold. Then we have physics, we have a detection model, and then we optimize. Very similar to what I did with the index. I try to find the maximum attack that doesn't trigger any alarm. And then I get the value. That's the y value here. So then I get these type of concave shapes. So basically, this is the room. As I change the detection threshold, this is the room the attacker has to fly under the radar, so to say. So here you have 4 different detection methods. So the support vector machines are lower, you see here, which means that it restricts the attacker more. So the blue curve here, that's the Kalman filter. So basically what it means is that if I set the threshold so that it only alarms on average if there's no attack, it alarms every 50 minutes, which is still quite a lot, but nevertheless. This is somehow how much maximum perturbation you can cause in a transient as an attacker without triggering the alarm. But you see that in this particular case, the support vector machine is restricting it better, and it's quite. But actually, the best detector is the one here, which is a support vector machine that is using the residual from a Kalman filter. So it's somehow a hybrid detection model. But this is actually a quite interesting metric, I think, that is useful in this context. Yes.
Do we have enough historical attack data to be able to train this?
I didn't do the training here. It was the competing team. I was kind of the control guy. We did the Kalman filters. We kind of lost here, although, of course, we gave our residuals to them. So they use, I guess the winning alternative was using that here. So they collected lots of data over time. I should say they did not allow us to do any attacks on the real infrastructure here. So this is a simulation. We got real data, so we could build a model. So it's simulated. So in that sense, we had all the data. We could generate as much data as we wanted. I think maybe it's. I think one interesting aspect here I want to point out. So a lot about what I've been talking about today is kind of model-based. It's assuming that attacker knows the model, etc. Although we had a good question here about, is it realistic that you know the Jacobian? Can you reconstruct it from data, etc. Here you really see a difference. So the blue curve is really detecting an attack based on a physics model. The SVMs here are only using collected data. And there's an interesting difference here, because operational data is more than physics. It's also user pattern. I mean, for instance, it would be physically possible that the temperature changes in the middle of the night. I mean, it can happen. I mean, there is a physical situation where that happens. But from the training data, I mean, you haven't seen that because people are not there. So if you build a detector based on such data, of course, it will be more. It takes in more than the physics. It also takes in how the system is being used. So that's my interpretation of why it restricts the attacker more. It can not only need it to respect physics in some sense, it also needs to make sure that it doesn't sort of deviate in what's the normal operating behavior. So I think that's the way to interpret these curves. So how it's being used then? Well, so the system used one of these detectors to trigger an alarm to say this sensor now is being anomalous. What happens then? What we did then was we used a Kalman filter. Whether you detected the attack or not using the Kalman filter, that doesn't matter. But once you have decided that here is a malicious data, what you do is that you have a Kalman filter. It's a state observer, so you have a model of the dynamics. You feed it with the data that you trust, and then you can predict the state of the system, and you can predict all the measurements, and then you can close the loop using that. Interest of time, I'm going to skip that. But basically what you see if you close the loop here is that here is the nominal header flow going out. Here is the attack starting, and the temperature goes down. If you don't do anything, that temperature will go down, and that will trigger the boiler to go up, and the attack is successful. Whereas if we use our system, it automatically, at this point here, it detects that this is anomalous. It doesn't fit. That the temperature has gone down and the header outflow it's not consistent with the temperatures in the room. So there is clearly some malicious manipulation of this sensor. So it uses the temperature in the rooms to predict backwards what is really the header flow, and then it uses that to regulate the temperature back. So you basically mitigate the attack. Yes. Yeah. Yeah. I think on the short time scale, maybe it doesn't matter so much, because I mean, even if it's just an equipment failure, it still could be harmful to the system, and the system will kind of automatically fix it. But I think the reaction it should trigger is very different, right? So because you need to fix it, right? I mean, you cannot let the system be in this state. I mean, whether it's an attack or a fault, you need to look into it. If it's a fault, you probably need to check the device. If it's an attack, you need to bring in the security guys and see what's happening. So I think on this time scale here, I'd say that it maybe doesn't matter so much, but it should trigger an investigation, so sort of forensics. And but it's a very good question that I get quite a bit. How do you distinguish between a fault and an attack? And I mean, sometimes it's really hard. I mean, an attack can try to look like a fault, right? For instance, it has an incentive maybe to do that. Often in the type of attacks that we come up with, we use optimization to find them, and then they become very, very particular, coordinated, both in time and space. So the probability that a fault would look like that is essentially zero. So that's kind of one way. So if some signals suddenly change in a very coordinated manner, then I'd say maybe it's more likely it's an attack than a fault. But on a short time scale, maybe you need to save the situation. You need to save the physics. So that's my best answer. Yes. Yes. Yeah. So this was one example of this scenario where we basically we measure the temperatures in the rooms and we save the day that way. So that's one way. I think it also was an interesting case study where we compared the more physics-based models with the data-based models. Yes. So that's part one. If you want to summarize this, it was a bit all over the place, a bit superficial maybe, but I think you got at least you got some idea what people are working on. At least our group have been working on. So security has become increasingly important in this area, and I showed you some examples of these incidents in the power, water, gas industry. And there's been dedicated malware for at least 10 years. And people talk about these advanced persistent threats, like nation states typically that has a lot of resources, a lot of time on their hands, and a lot of knowledge. I also want to say that I'm not saying that we should throw out IT security. I really think that one needs to think about how do we deploy encryption, authentication, all of those tools. They should be in our systems in a safe manner, but it's not going to be enough. Because securing one sensor link, it's not going to secure the overall control system. So often people talk about defense in depth. So you should have many layers of defense. The controller should take these fault scenarios into account. They should be able to reconfigure if some sensor doesn't really fit the pattern, etc. So that's how to think about it. And I think a careful and repeated risk analysis is a good way to think about it. I also want to say that I think there's been several questions about this, the attack and operator modeling. It's really, you need to think that through. A lot of the solutions, so when you create an attack scenario and then you optimize, you get a solution often. Especially in these type of security problems, the answer is very sensitive to the assumptions you make there. So, for instance, there are schemes where you do voting. You collect all the sensor data, and then you do voting to see the majority of sensor values. You're going to take the majority, and that's very robust as long as not more than half of the sensor values are corrupted, right? But if one more than half is, then everything fails. And similarly with the encryption, right? If nobody knows, I mean, if the password leaks, you go from having perfect security to nothing. This is typical here in these security problems, that if you just make an epsilon perturbation to one of the assumptions, it can really just break. So that's why I try to talk about this scenario. It's really, if you just changed it a little bit, the utility function or the resource, it can really change the situation. So it's important when you do the risk management that you kind of, some of these assumptions, and you should sweep them to see a bit what happens to the solution. That if it's a very fragile point, maybe it's not really the best place to operate on. And you saw 3 case studies. And dynamics matters, and this is something we will see more next. So what I will do now, I will go into some more depth into the attack modeling and anomaly detection, unless you have any more questions about this part. We'll see how much time we have. I'll probably not have time to go through everything. Yes? Yes? Should we be nervous? Yeah, I think we should. But I mean, there's lots of reasons to be nervous these days, I think. So this is one of the things to be nervous about. I mean, just a reflection about, for instance, Ukraine. I mean, there were cyber attacks against the power grid for many years before the war started. I mean, they did some harm, but they recovered. I think it requires relatively large resources, and I think the impact of those attacks was maybe not as large as one maybe would have feared. I mean, they were able to put the grid up in a few, maybe not hours, but in a few. I mean, they could recover. So I think these type of attacks requires a lot of resources, and if you want to break systems, I mean, it seems more like military attack. I mean, the bombings that we see now. I mean, that's more effective. But there is a big difference, right? Because these type of cyber attack, it offers the adversary some sort of deniability. You can, I mean, for years you can carry out these type of remote. You can sit in your office and start to annoy your adversary, and you can deny, you know, we're not doing anything. There's no, it's very hard to see who did it, and so on. The impact might be limited relatively, but it's still there, and it's annoying, and who knows what the impact will be. So I think that's the real fear. It's in this. So I think to get really dramatic impact, maybe you need a physical attack as well, but it could be coordinated, of course, with this. One could imagine a physical attack, and simultaneously you do a cyber attack against the monitoring system that will delay the response, etc. So it's there's many aspects here, but I would be a bit nervous, yes. Yes. So this is what I was planning to talk about. A little bit about denial of service attacks, and then false data injection attacks, and some estimation problems. The main reference here, it's these lovely lecture notes by my colleague Shreya Sundaram at Purdue. I really recommend them. They're very, very clean, and so it's really the main. I use it in my course. I also have some lecture notes. I think they should be made available to you in the download page. And a bit of a disclaimer, what's to come here. This is another very famous control scientist, Bart de Moor. This is because it's going to be a lot of linear algebra now. And according to Bart, you know, that's the only thing we really understand in this world. And I also want to, this is a tweet I found some time ago, I don't know. So Peyman Milanfar, I think he's the chief scientist at Google, so he's also a big fan of linear algebra. So this is just to say that there's going to be a lot of linear algebra now, and I think it's quite useful to understand actually what is happening. And I know that real systems are nonlinear, etc., but I think it's always a good idea to look at the linear situation, especially if it's high dimensional, to try to understand what is going on. So this is kind of the figure we're going to work on. So we have a plant, we have a controller, there is some sort of alarm infrastructure. It could be a bad data detector, like the one we talked about before. It looks at the received measurements and also the control actions, and it tries to figure out if the data is sort of consistent with the physics. And then in the network that separates the plant from the controller, there could be an adversary. And we talked about CIA, confidentiality, integrity, and availability. So confidentiality would be that somebody reads the data. Availability would be that somebody's opening a breaker. And integrity would be that somebody manipulates the data. So let's look at the availability attacks. What could that mean? So that's something like this. And in this, following now the advice of Bart, we're going to use linear algebra to model things. So I'm going to use a very simple model of the plant. I'm going to use what's called a linear discrete time state space model. I don't know how familiar you are with that. But it's really K, so it's discrete time index. So X now is it's a vector of all the internal states of the plant. So if it's a power grid, it can be the voltage levels in the nodes, etc. So A now it's the system matrix. So it basically shows that if the system is not under control, it's just how the state evolves over time. I'm not sure how familiar you are with this type of modeling, but how do you come to the matrix A? Typically what you do is you take your ordinary differential equation, you write it down, you do your homework, write it down, you find an operating point. For instance, the water tanks, they operate at that level. You linearize it around that level. You take the Jacobian, and then you get a continuous time linear state space model. And then you can sample that, and then you get this A matrix here. So that's how you get the A. B is how the control is affecting the dynamics, so it measures now how the attack goes there. So a very, very simple and crude model of a denial of service attack would be something like this. So denial of service attack is it's one attack that you carry out to break availability. Typically, you inject a lot of false traffic in the network so that the control commands it's not received. So in this scenario, it means that the circuit breaker is open. It often has this characteristic of randomness. You inject a lot of data traffic, and so one very simple model is something like this, that with probability P, the control is being actuated. This is a feedback control, so that's what's the action of the controller here. So K is the action of the controller. It measures the state, it computes U, and it's being transmitted. And with probability P, it reaches the plant. And then it says here with probability 1 minus P, you drop it. So that's when the attack is active. And then you can prove things like the following. That under these type of attacks, you can prove that the expected value of the state of the plant is going to be bounded if and only if the spectral radius of the A matrix here times the squared times the drop probability, if that's less than 1. So that's the type of results. Why is this an interesting result to tell you? Well, so what's the spectral radius? That's a measure of how much the dynamic inflates the state space, so to say. It's a measure of instability. So if the spectral radius is bigger than 1, it means that if you have no control, the system is starting to diverge. So it can be an unstable airplane or something like this. So rho is really a measure of how difficult my plant is to control. And of course, it also then gives you a condition for how intense denial of service attack you can tolerate in order to stay operational here. It also has this interesting implication that if the system is unstable, it's of course much more critical. But it also shows you that if this plant is stable, it doesn't really matter how many packages you drop. You will not, the state will still be bounded. But this is of course just to say that a plant that is stable already by itself, I mean, of course, if you just open the feedback, it's going to be stable. That's the only thing it says. It doesn't mean that the attack is not harmful. It just means that the state is not going to blow up. But the control performance might be quite bad. So here is one example. So fortunately I didn't have time to come up with a good power systems model, but this is taken from these excellent lecture notes by Shreyas. So here you have a typical example from it's an airplane model. So the state here is the vertical velocity, it's the pitch rate and the angle of attack, etc. And here you see the A matrix. So it's a 4x4 matrix. Here you see the B matrix. There are some measurements. You measure the velocity and the pitch rate. And now you can simulate this type of to see here what happens. So this is a case, for instance, where you drop no packages. So here the control system is taking the system from a 0 velocity to going up with a velocity of 1. And and then you see that this is how the nominal system works, and then you add a drop probability of 10%. In this particular case, you only drop one packet by chance, but you see already only dropping one single packet here creates quite a big disturbance here. Here I've increased it to 30%, and you see here the drop randomly come, and you see the control performance is it's a pretty bumpy ride, let's say. This particular example is, if you look at, of course, the big question is what is rho? What is the largest? So rho is the largest, the magnitude of the largest eigenvalue of the A matrix. What is that here? It turns out it's 0.99 for this model. So this airplane is actually an old plane, so it's stable by itself. So it doesn't really matter how large Q I make, it will not be unstable. But still you see that it gets a pretty bumpy ride. So I also gave, I think I sent to Alessia a little script here. If you want to simulate this yourself, I can just show you. It's this denial of service F8. So it's just using some relatively basic, see if I can make it work. Doesn't seem like I have a computer with me today. There. Of course, it's a demo daemon here. Let's see. Seems like something interesting happened when I connected my computer. Let's do it again. There. Okay, now I think it works. Yeah, so what it does here is first it imports some packages. It's NumPy. It creates the model of the airplane you can see here. To make it a little bit more interesting, I introduced a destabilization factor here. So it's a scaling of the dynamics to make it more. So let's take it 20% more unstable to make it more interesting. And then it designs a state feedback controller to stabilize the dynamics. This is the nominal dynamics. Can you see my? Yeah, you can. So this shows the controller is trying to regulate the velocity vertical. And then here you can go in and look at the response under denial of service attack. And then you can go in and play now with the drop probability here. So if you remember now, I made the system a little bit more unstable. So then you see here with 20% drop probability, this is what you see in the trajectory. Here you also see the product, the spectral radius squared times Q. So it's 0.28. So it should still be fine. But if we increase the drop probability a bit, we'll see here it's still 0.86. Remember, when it's above 1, that's when you should start to see bad things. So let's do that. So yeah, here. Now you see that the product is 1.15, and then you see that the trajectory diverges. So then basically you have destabilized the plant. So that's one typical result you find in the denial of service. You can sort of find what's the maximum drop probability over a channel you can tolerate without sort of getting instability. But even if you have stability, like in this case, the question is if you want to sit in this airplane, right? It's still a pretty bumpy ride. So I mean, there are many what you care about. So. Good. Good. that's what I'm going to say about availability attacks. There's other type of approaches in the literature where you do more worst case. Instead of doing random drops, you look at how long you try to optimize duration of outages and do in a more deterministic setting. That's of course also possible. But I'm not going to talk more about that here. Instead, I'm going to turn to integrity attacks. So that's really the situation where the attacker is either injecting false measurements. So that's exactly the situation we had in the power grid. Or it affects the control commands. So the controller thinks that it applies 1 volt, but instead, in fact, what it did, it injected it's exponentially increasing, right? So that would be an example of that. If you model that in this particular scenario, you could still use this model that we had before. Now I use the notation U tilde. So U tilde here is supposed to indicate that the signal being applied to the plant is not what the controller thinks. So UD is what the controller thinks it is, but it's been manipulated with IU, and then U tilde is being applied. Same thing with the measurement. What is being received here is not the true measurement, YD, but it's actually something corrupted. So that is what this notation is supposed to mean. So the detection problem here is really, how do I think about this problem in a dynamical setting? I receive this Y tilde and I have this UD. How and when can I design detectors that alarms if there are such perturbations? Can I write down conditions when this happens or not? And that's why I insist on doing this in a linear scenario, because that you can turn into a linear algebra problem. So there you can analyze the situation completely. And as I said, if you can approximate your real system locally using this type of models, then you have a very good understanding of how things work. Here's another example. It's a speed control system of a car. It's also taken from Freya's book. This is essentially Newton's, the dynamics is really saying that the velocity in the next time step is equal to the velocity you have now, plus the acceleration times the time. So it's really Newton's law discretized in time. So it's nothing more than that. It's a PI controller trying to regulate the velocity of the car. Then I'm going to inject some false speed measurements. So the speed controller is not measuring the true speed, but something else. I guess it could have also been, I should have made it into a generator spinning, right? It's basically the torque applying, if you like. And then there's an anomaly detector trying to figure out whether something bad or not is happening. So here is, again, some simulations. There's another script you can play with just to show you what happens. So here, the desired velocity is 1. The speed of the car goes up to 1. So that's as it should. At time 15, there is an attack. So suddenly somebody imposes a sinusoidal signal on the measurement. And you see what happens is, what you see happens is, of course, that then the speed controller will start to react on that. So the car will start to oscillate like this. The good news is that the detector I have installed here is able to reconstruct the attack. So this is the detection signal that comes out. So you see before the attack it's 0, but here it reacts instantly. So it can basically say instantaneously that so that was a good situation. Here's another situation when the attack is just a bias. So at time 15, suddenly it injects a bias. So interestingly enough, this is the detection signal. There you don't get something persistent. So the attack just goes on and on and on and on. But the detector just gives you a blip when the attack starts, and then it goes away. So that is kind of interesting. So anybody has any idea what that, where that could be? Yeah. Yes. Yeah. Mm. Mm. Yeah, I mean, it's definitely sensitive to sudden change. But it has to do with the zero dynamics again, because there is some sort of zero dynamics in this feedback control system. It's not maybe so super easy to see, but it has to do with zero dynamics, that these biases are constant signals lies in the sort of in the zero, in the null space of the closed loop system. If you make a sudden change, that's not physical. So that's why this is really why you see a bump here. It's not physical that suddenly the velocity goes from 0 to something. I mean, that is not. So that creates a bump. But in the steady state, they're both sort of physical. So that creates. So that's why it dies away here. So that's somehow the superficial. So it has to do with the zero dynamics here. This is just to say that also in these trivial examples, there are some sort of scenarios that are not so easy. You can play with this also with this Python script there, but I'm not going to show you that now. Yes. So let's think about the detector. How should we design the detector here? So what I'm going to do now is I'm going to assume that this desired control is known, which is not so strange. I mean, we sit next to the control system. We can just look what the controller says. And then I'm going to use linearity and subtract this information. So I'm really just going to look for what I don't know. And since system is linear, I can always subtract such information. And maybe the notation is a bit unfortunate, but this is really standard, at least if you use these lecture notes. So I'm going to collect everything I don't know in this vector u. So in this case, it's attacks on the input or attacks in the outputs. So I'm going to say that's a vector in Rm. So I'm going to try to decide when can I say that such manipulations are present or not. So using linearity and eliminating everything I know, then I can write the dynamics in this form. So I have the A and B and C and D. And U now is this unknown input. And then generally what I assume that is that the operator, he knows the physics of the model. So A, B, C, D, he has done his homework, written down the model, and it receives the measurements. What I don't know typically is, of course, if there's, at least not yet, I don't know if there's an attack or not. And I often don't know the internal state X. I measure some of them here, right? C times X. But often, I'd say in the power system example I had before, I had many more measurements than states. I'd say that is not the typical situation in a control grid. You usually have you have fewer measurements than state. So the problem I'm going to look at now is when, with only access to the model and a sequence of measurements, when can I decide when there is a perturbation or not if I don't know X? And that leads to a sort of a sequence of type of estimation problems you can formulate, ranging from the simplest one to the harder one. So the first one is more or less a classical observation problem. How do I estimate the state if I happen to know y and u? How do I estimate u if I know y and x0? Estimation of u and x from y, that's what's called strong observability, and then asymptotic estimation, that's strong detectability. So there's a whole range of type of scenarios depending on the assumptions you make here. And what is nice here is that you can all turn them into a linear algebra problem. And all of these results go back to the following I'd say, classical result. I don't know if you have seen this before. So if you have a linear equation of this type, y equals cx plus du, you can ask the question, is there an x or u? So x is in Rn and u is in Rm. Is there an x and u that can explain the measurements? And that's true if and only if the rank of C, D, Y is equal to the rank of C and D. Have you seen this before? Yeah, trivial. Yeah, I don't have to explain that. So that's how do I compute such a solution? Then you can use what is called a pseudo-inverse. So that is one result that is being frequently used here. The second one is to say that if there is a solution, the solution U is unique if and only if the rank of C times D is equal to rank of C plus M. So M is the number of unknown components. Is this also known? Should I make a figure? Let's see what I had in mind. So assume, for instance, we have two measurements. There's one state and there is one disturbance like this. If it so happens that the direction of D points in that direction and C points exactly in the same direction like this, then you see that the rank C dy is equal to what? Two, right? The number of dimensions these span together, right? C and D, they all span one dimension, Y spans a different dimension. Is there a solution to the problem? U1, is this equal to rank CD? Well, rank CD is equal to 1, right? So no. And that's what you see here. There's no X and U that can explain this. So typically when you use this type of result is that you want to, if you receive your measurements, you want to see, can my model explain the data or not? If not, it typically means there's an anomaly. Something in the data is not explained by my model, so that should trigger an alarm. So that's where you use this. So that's why it's not consistent. Consistent with model. So this was U1. The second result, let's just take that as well. 1 or 2. This is a better scenario. Let's assume that the direction of the disturbance is in that way, and then the direction of the state is in that way, and then the measurements is like this. So this is Y. And here you see that rank C, D, Y equals to rank CD equals to 2, right? So Y is consistent. Right? Because there is a linear combination of there is a state and there is a disturbance that can explain my measurement. So here I could say, okay, this measurement is consistent with my model, but I cannot only explain it with the state, right? So remember, so X is the normal. This is my normal dynamics, so to say. That's the normal physics that I should expect. But this Y, it can only lie in the C space to be normal. Now it's actually, there's a component pointing in the D space. So this means, oh, there must be something else here. So that's how you sort of use this type. Yes, exactly. That's what it means. So you remember, U here means it's an attack. So in this scenario, you would trigger as soon as Y is pointing outside of C. That's when you would. So you would estimate. So this is U1. U1, right? We can also use U2. U2 would be rank C of D should be equal to 2. And in order to U2 to apply, we should say that it's equal to rank of C plus M. Rank of C is equal to 1, and M is equal to 1, right? So this is fine. This is 1, and this is 1. So if you want to put a check mark, this is okay. This is okay. So U2 is okay. So here we can, U is possible to reconstruct from Y. And how would you do that? Well, there's many ways. Maybe the easiest way is just to say that U hat is equal to 0 identity, and then you would multiply with the pseudo inverse of CD times Y. So you do a pseudo inverse on the measurements, and then you project it down to U, and then you would get your estimate here. So yeah, this is just to make it sort of these results likely. And of course, in dimension 2, this is almost trivial. But as you will see, you saw already in the power systems case, actually in the power systems case, it was very much like this. It was a static model. See, there's no A here. And remember there, Y had dimension 500. So it's a 500 dimensional vector. And you're going to think about, and you had 118 states, right? So Xn was 118, P was 500, and so on, and then there was some disturbances. So in such cases, it's quite helpful to use these type of linear algebra routines that can really tell you exactly what directions you can look. Yes. Yeah. Yes. Good point. I mean, in practice, what you do typically you look at the singular values. If you're familiar with singular value decomposition, you look at the singular values, and often what you see is that there is to have exactly a rank deficiency, some of the singular values should be exactly 0. And they're not going to be that for numerical reasons. But they're going to be, often if you plot them, you see there's a dramatic drop at some point. So the numerical rank, the effective rank, you can, if you see, like, you plot the singular values and you see a significant drop, that is a measure of the sort of the real rank of the system, even though that numerically it might have. So that's my best answer. Yeah. Yes. Coming back again to this risk modeling, that's the attack scenario you're looking into. So depending on how you set up the framework. So in this, what would D be here? So D would be D measures where the which sensors are under attack, or which sensors do I think are under attack. Maybe some sensors I think are immune because I have encrypted them or something. So I think those sensing measurements are fine. So I exclude them from D. Otherwise, if I think all the sensors are under attack, then I would choose the identity matrix. So it's really about how I want to model. And that's also how you can use this result, right? Because if this result is not true, it means that your model is not able to explain the data. So your attack model is not able to. So that's one way of, yeah. Yeah, so sample applications. So U1 is really, is my model, can my model effectively explain what I see or not? Otherwise, if not, then I need to reformulate the model. And the second one is really, is there enough, is the model able to uniquely tell me what is going on in my system, or do I need to refine it? Now I need to speed up a bit here, I see, so I'm gonna go pretty quickly. So what is nice now with this framework is that we started here with this dynamical system, but you can now apply this recursively. So if you have a history of control actions, you can just recursively apply these equations, and then you get a linear equation of this type. So you see that the state at time k plus 1 is the same as the state at time 0, and then you multiply with a times k plus 1, and then you get what is called a controllability matrix times the history of controls. So what you have here is really a linear equation. So it's dynamical and so on, but if I fix the time horizon, it really becomes an equation of similar. If you interpret C as AK plus 1 and the D as CK, it's really a linear equation, right? So as soon as you sort of fix the time horizon, it becomes a linear equation. But of course, the dimensions now start to grow very, very quickly as the time goes up. So let's just look at some of these problems, how you can solve them. So this is the estimation of x from y and u. So this is a little bit counter what I said before, but let's start easy. So let's say y0 by definition is equal to c times x0 plus d times u0. The next measurement is equal to c times a times x0 plus cb plus u1. And I can do this for a time horizon 0 to L. And I can stack this into linear equation of this form. So assume now, for instance, that in the best scenario, I actually know there is no attack on the input, so I know exactly what the input is over that time horizon. I know what measurements I received. The only thing I don't know is where the system started. I don't know the airplane's initial velocity or something like that. The question is, by the way, this is what is called the observability matrix over horizon 0 to L, and this is called the invertibility matrix. It has a very nice tuplets structure. But this now maps really to these rank conditions. When is there a solution to this problem? Well, if you just rearrange the problem, so what you know, you put on the left-hand side. So this you know, and you know this entire guy here. So you have y minus the invertibility times u, and then you want to solve for x0. So when is there a unique solution x0 to this problem? Well, that's exactly the case only if the rank of this matrix is equal to n. And that's, people say it's observable. So what it means is that if the system is observable with L, then it means if you have L measurements, you can reconstruct. You take L samples, and then you can reconstruct where you started, assuming you knew the input and the output. And that's a classical result you probably have seen in one way or another if you've taken a control course. What is nice is that you can ask, how many samples do I need to take? Should L go to infinity? What is nice is that L, you never need to check for L larger than n minus the rank of C. If this condition is not true after n minus rank C steps, it will never be true. So you never need to wait longer than that. If you cannot reconstruct the initial state, then you're done. So that's the delay. So there's a delay here. You need to collect some samples, and then you look back in time. Exercise, I jump that. So let's move on. Here's a little bit more interesting example, maybe. So here I flip things around. I know the measurements. I know the initial states now suddenly. But now I don't know if there was an attack. Of course, I don't know any of the attacks, but maybe I think that's it's a little bit too much to ask to reconstruct all of the attacks. Let's see if I can reconstruct the first one. Just to start from there. So this is again a linear equation. You can again apply the rank condition. So you're rearranging again. You collect what you know to the left, the measurements, and you know the initial state. And you want to search for the component of U here. And you ask, when can I uniquely solve for U0? Well, using this condition U2 that I just had there, it says that that's possible if and only if the rank of the invertibility matrix is equal to the rank of the invertibility matrix reduced. So you see it has this recursive structure, so you need to take away one sample plus M. And M is the number of unknown components in U. So that's, you can reconstruct, you collect L samples, and then you ask, is it possible for me to say what the attack was L steps ago? That's possible if and only if this rank is true. And again, remember now that the dimension here is, what's the dimension of L? It's L plus 1 times P. So the dimension starts to grow very quickly here. And a nice theorem here says that if this condition is not true for n minus the nullity of d plus 1, it's never going to be true. So how much delay should you check? This is the maximum delay. If the system is not, if it's not possible for you to reconstruct after those many steps, it will never happen. So then you need to go back to the drawing board. You need to put in more sensors. If you really want to know U0, you need to do something. So it's both interesting from a point of view of building the system, because it tells you what is possible to do or not, but it also gives you a recipe. Because if you want to reconstruct U0 here, you can just use the pseudo inverse. It will give you the answer, right? So it's both in both. And of course, if you're interested in U1, you would just shift the time horizon step by step. There's also a nice result here saying something about the rank condition of the state matrices. I'm jumping from that. There's another example. I'll skip that. Here's the third variation. This is closest to the real example I'm interested in. So the only thing I know is the measurements. I have no idea where the plane started or where the system started, and I have no idea what disturbances there are. When is it possible for me to reconstruct both the state and the input? Well, same story again. You can just apply U2, and it says that this is possible if only if the rank of this combined matrix is equal to the rank of JL plus N. And people say then that the system is strongly observable. So that's a very, very strong property, because it means that after L time steps, you take L measurements, and then you're able to say exactly where the system started and exactly what the disturbance was at time 0. And it's an if and only if statement. And again, there's a result saying that if this result is not true for n steps, it will never be true. So again, if this is a property you like, then you really need to check it for n, L equals to n. If not, then you're basically not going to work. Yes. And there's a condition here. So if you're familiar with zeros and poles of systems, this condition you can show it's equivalent to that the system has no zeros at all. This has to do with this zero dynamics that I was talking about. So a system that has zero dynamics, this can never happen. So you need to put in as many sensors that all zero dynamics is gone. That's what this means. And finally, problem 4 is asymptotic. So if the system is not strongly observable, let's say that there is a zero, that means that you cannot reconstruct the state and the attack after L steps. It's never going to be possible. Then you can relax and say, well, is it possible to do it eventually, like exponentially? And then you can do something, and this is what is leading up to what is called unknown input observers. I think I will, in the interest of time, I will go through this very quickly. What you get is the following. You get a recursive estimator. So instead of having a linear equation that you stack the measurement, you recursively feed it with receding measurements. And what you can show is that this x hat will converge if and only if the system zeros are inside the unit disk. What that means is that the system is minimum phase, if you've heard that concept from control system. Minimum phase systems are systems that have stable zeros. So if the system is minimum phase, you can always do this trick. So then you can asymptotically converge to the right answer. And there is a nice comparison to the regular Leuenberger observer. David Leuenberger passed away. Actually, I heard the other day. It's a big name in our field. He invented the classical observers. Just to point out the difference, in a classical state observer, you assume that the input is known. So compare the difference now that here really the input is unknown. So that's why we have stronger. We need to add delays. We need to stack some measurement over time because we need to first reconstruct U, and then we need to reconstruct X. So that's why it's a stronger condition here. Yes. Lots of equations. This is from that's another script you can play with where I designed a state estimator for the airplane. So what you see here is this estimator in action. So when you start time, the operator has no idea where the airplane starts, and it has no idea whether there's a disturbance or not. And then you recursively apply this method, and what you find is that you get an exponential convergence of both the estimate of the disturbance and of the state. And there's some freedom there to tune this. So that's kind of a nice property. Yes. I think maybe my time is more or less up. Just to say, I have 3 more slides maybe, if that's fine. Yes. All of this is covered in great detail in this really lovely notes by Shreyas. So it really goes back to these ideas on the rank, and I think you can find use of it in many situations. I just want to say a few words because this is all a little bit ideal. It's assuming that there is no stochastic noise in the measurement. I think I got one question for Thomas there. What if there's non-ideal devices in the system? So so instead of just looking at the state estimate, you need to take into account that there can be a little bit of noise in the measurement. So how do you deal with that? So, I mean, this U hat, it will never be, even if there's not an attack, it will not be exactly 0. There will be a little bit of noise there. So how should you trigger on that? And here, my big recommendation is not to just use a simple threshold test, because that's going to trigger a lot of false alarms. It's really to use this called cumulative sum tests. That is so the simplest test you could do is these type of chi-squares test. You take the signal you're looking at, you square it, and you say if it's big enough, I alarm. That's going to give you many false alarms. But the cumulative sum test, you add a memory. So you take the old cumulative sum, you add the residual, and you remove a bias. And this type of test has a much better trade-off between the time to alarm and the reducing the false alarm rate. So that's a very, if you want, it's very easy to implement. It really gives a big difference in the number of in this trade-off. So that's a good thing to look into if you're going to implement this in practice. So I recommend you to look into the QSUM. Yes. I think I'm going to skip the PCA. So what you've seen here is some of the tools we've been using. Denial of service, how to model it, and especially how it can cause instability, and then this FDI attacks and how to detect it. So the trick here is really to reduce it into a linear algebra problem, because there's a lot of tools available there that can help you, both to sort of offline do risk management, where should I place sensors, etc., but also online, how do I actually do the estimation? So that's a tip. And for noisy data, check out these QSUM tests. They can really give you a big help. And then I got some questions about this in the break as well. What if you don't have these models? What if you only have the data? And that was what PCA was a little bit about that I skipped. There's usually two ways to think about it. Either it's the indirect approach or the direct approach. The indirect approach is that you collect the batches of data and then you do what is called system identification. You try to estimate the ABCD from, and that's, I'd say, the classical way to do it. Then there's the direct approach where you really just uses the tons of data they have collected and go from there. And that's of course very popular nowadays in using machine learning and so on. That's another way to go. My experience with that, it's those tools are quite good at detecting anomalies, that something is wrong, because they're very good at finding a pattern. But when it comes to figure out what did go wrong, if you want to understand what's the underlying cause, if you want to control a system safely, you want to do something. There's a fault, but where is the fault? What should I do? And for that, in my experience, you need to have some more model knowledge. You need to know a little bit how the system is hooked up. How can I explain what I see? Sure, it's not as it should, but why is it not as it should? And to do that, in my experience, you need a little bit of sort of underlying knowledge of the system. So for that's what I mean by this final sentence here. That to reconstruct a tax fault, you need some model knowledge. Yes. Apologies for running over time a bit, but I'm available for questions, and you have the slides, and there's also some scripts that you can play with if you want to learn a bit more. So with that, I'm done. Thanks.
Maybe a couple of questions to Henrik. Please.
Just let's go back to just so I answer the right question. I think you're referring to this database. Yeah. I'd say a lot. I think this is really, so what I've been presenting is maybe the academic side of things. So it's problems that are tractable to nice mathematics that we like to do. this database is really on the other end of the spectrum. This is really attacks or faults that have been observed. This is much more IT. You can read here more. So these ones, I'd say that the manufacturers really needs to take into account. There's many more regulations coming in place that they need to address. I think these are based on actual incidents, I'd say. I don't think they typically say where it has happened or so. It's because operators are usually not too keen on telling what has happened, but they need, I think by law, they need to report something. So these attacks here, they are very. What you will find is that they may be quite generic, so to say. So you don't know exactly what has happened. Sometimes because it's actually hard to understand. These systems are very complicated, so it's very hard to know exactly what did happen. But I think this is if you want to get a more practical view of things, this is a good place to start.
Other question? Yeah.
N. What is N? How do I build M? Yeah, that's again the attack scenario. So when I do my risk management, this is the attack scenario I'm considering right now. So C here is somehow that's the physics. That's what I have to live with. The D here is the directions I'm currently investigating. So yeah. So for instance, if I choose this D, this is one attack scenario, then I'm able to explain this measurement. So this model I can explain, but then I need to have an attack. Here's another attack scenario. So here the attack is aligned with the physics. So if I get this measurement, it basically says that, well, it doesn't really fit your model. So you need to think, you need to remodel. This is also actually an example of where U2 fails here, because just as an example, let's say that this is the physics model and the attack model, and then the measurement is this. It's perfectly aligned, right? But I have no clue what is. I cannot. I can explain this using the physics. I can explain it using an attack. There's infinitely many solutions, so it violates U2. It will not. I will not be able to explain that uniquely. So that's not really a. For the operator, it's not really a good situation, because I cannot not tell X, I cannot tell you. It's well, I can say that it's consistent with my model. That's the only thing I can say.
Yeah. Well, let's see if there's any other question. If not, I'll get back to you. Okay, maybe quickly, Disha.
But how do you determine the dimension?
Oh, M. Yeah. Yeah. So that's another very good question, and it's those type of questions that led us to these type of attack space. So this is what we call disruption resources. That is how powerful the attack is, and one very easy way to think about it, it's actually the dimension of M. How many degrees of freedom the player I'm playing against. So if M is equal to N, or even bigger, that would be a very, very powerful adversary. So it's again, it goes back to this scenario I'm investigating. And the thing is, I mean, if you're giving enough resources to the attacker, he's going to win, right? It's so the question is a bit, and of course, you as an operator, you don't know. So that's what I said, that you should not consider one scenario. You should see this as tuning parameter. As you sweep these parameters, you know what happens to your defenses. If there's a drastic change at some point when you change the scenario a little bit, then maybe that is an interesting. It's worthy of investigation. So of course, these are just you're guessing who you're playing against.
One final big question. Big picture question from my side. So here you're talking about dynamical systems that comes from they are physical systems, but I guess also there are a good number of people here also working on financial systems or markets, and I guess also one can define them as dynamic systems. One can define matrix A. So are you aware that whether the nice tools that you showed us today coming from linear algebra also can be implemented to identify any attacks in financial systems, in the stock markets, I don't know, or electricity markets? Are you aware of that, or do you think that these are useful tools also there?
Yeah, I haven't worked on that myself, but I mean, like just thinking about solutions to these optimization problems, you use some sort of gradient descent. I mean, that's a recursive equation of this type, and of course you can apply these type of tools in that scenario as well. And I would assume that somebody has looked into that. So, I mean, as soon as you have these dynamics, x k plus 1 equals ax k. I mean, you can use everything here, right? It's yeah. Thank you.